So in this video, we're going to look at a couple examples of how to use the binomial distribution. Remember from the previous video that each trial only has two outcomes in a binomial distribution, and we call them success or failure, or success or not success. Remember, these two are complementary events of each other. So the probabilities add to 1. So the probability of success is constant for every trial. We call that P. So that means the probability of not succeeding or failure is 1 minus P, complementary events. All trials are independent of each other and specific order is not required. So let's see how we use it, remembering that the probability of X equaling a particular value is given by NCX, P to the power of X, Q or 1 minus P to the power of N minus X. So let's give it a shot. Find the probability of landing 4 heads. So when a fair coin is flipped 6 times, correct it to 4 decimal places. So let's define it. And so X is binomially distributed with N being 6 and P being 1 over 2. So I was looking for the coin. Now, I know it's binomial. Why? First of all, you have 2 options. You land ahead or you don't land ahead. There you 2. We know the probability of landing ahead on a coin never changes. That's our second condition met. We know that landing ahead the next time is completely independent of the one beforehand. So that's our third step. And it hasn't asked anything to do with order. It just says 4 out of the next 6. So therefore it's binomial. So I can confidently say X is binomially distributed with N equals 6 and P is a half. So what I do now is I use my equation. So the probability of X being equal to 4, which is what I'm asked for, is 6, that's N. Our N value is 6. That's N, that's P. C4 times P, which is a half to the power of 4, times by 1 minus P, which happens to also be a half in this case. So I could just write a half. I might do 1 minus a half here to remind you. And to the power of the number of successes. Now, failures. If I have 4 successes, must be 2 failures. And from there, we then do some calculations. So 1/2 to the power of 4. This is actually 1/2 as well, to the power of 2. So that gives you times 1/2 to the power of 6. By index laws, doesn't always work out this way, but because the bases are the same, we can do that. Now 6C4, we've got a calculator. We're doing decimals, but we can also check it out with this. Is 4 factorial and 2 factorial. Remember, these two numbers must add to the 6. Now 6 factorial we know is 6 times 5 times 4 times 3 times 2 times 1, which I can simplify as 4 factorial, like that. The 4 factorials cancel. 6 times 5 is 30. 2 factorial is 2, so that gives you 15. And then we end up with 15 times 1 over 2 to the power of 6. And we calculate that to 4 decimal places as 0.2344, rounding it off correctly. That's how we use it. Let's have a go. Another example. A bag contains 4 blue balls and 3 red balls. A ball is selected, its color noted, and returned to the bag. It's done 5 times. Ooh, 5 times, that must be the trials. We've got 7 in total in there, so probably getting red is 3 over 7 and blue is 4 over 7. Okay, they're complementary events. So now find the probability of obtaining 2 blues, then a red on the first 3 selections. Okay, well, let's carefully check. Probabilities aren't changing. Yeah, that's good. What's happening is independent because it's being put back in every time. That's good. We've got 2 options, blue or red. That sounds all good. But the problem is it can't be binomial because there's a specific order required. All right, so our first 3 conditions have been met. So it sounds binomial, but there's an order. So no, can't be binomial. So blue, blue, red is going to be 4 over 7 times 4 over 7 times 3 over 7. Which when you simplify that, you get 4 times 4 is 16 times 3 is 48 and 7 cubed is 343. Okay, so specific order means it cannot be binomial distribution, so ignore that. The next one, though, let's look at it. Find the probability of obtaining 2 blue balls out of the 5. Okay, 2 balls out of the 5. There's no order. All the other conditions were met. Now the order condition is gone as well. So we want probability of x equaling 2. But what's x? We haven't defined it yet. So let's define x. So x must be binomially distributed. N equals 5. And the probability of getting a blue ball is 4 over 7. That's a probability of success. So here we go. End it with 5. N is 5. Choose 2. 5 trials, choose 2 of them to be successes. Times 4 over 7 squared times 3 over 7 to the power of, all 2 successes, therefore 3 failures. 5 choose 2. Over here we can calculate it as that. Now 5 factorial is 120. 3 factorial is 6. 2 factorial is 2. So that's all going to give me 10. So you get 10 times by 4 squared, which is 16, times by 3 cubed, which is 27. While I write 37, 27. That's all over. Well, that's 7 squared in the bottom there, 7 cubed, so 7 to the power of 5. And you'll be typically be asked to do it in decimal places. I forgot to put a condition here. Of course, in the exam, if it didn't have decimal places, you would have to make sure you left it as an exact value. But in this kind of case, they would do one of two things. Either they would say to write it in the format like a over b to the power of 5 or something. So, or maybe ab squared over c to the 5 and tell me what a, b, and c are or something like that. In which case you could have 270 times 4 squared over 7 to the power of 5, because 27 times 10 is 270 or something like that. But most of the time, if the number's getting big like this, they'll be asking for decimals. I just forgot to put that in there. Next one, find the probability of obtaining less than 2 balls. So probability less than 2. So x is still the same, so less than 2. That's the probability of 0 and the probability of 1 happening. All right, so probability of 0 happening is 5 trials, select 0 successes, times 4 over 7 to the power of 0 successes, times 3 over 7 to the power of 5 failures, plus 5, choose 1. So 5 trials, choose 1 success, times 4 over 7 to the power of 1 success, times 3 over 7 to the power of 4 failures. And we can simplify there. 5c0 is 1. Anything c0 is 1. 4 over 7 to the power of 0 is 1. So we end up with 3 to the 5 over 7 to the 5. Plus 5c1, well, nc1 is always equal to n, so 5c1 is 5 times 4 times 3 to the power of 4 all over 7 to the power of 5, because 7 to the power of 1 there, 7 to the power of 4 will be there, and you get that. And I'm going to, again, chuck them together on the calculator and see what I end up with. A good YouTuber would have done this earlier and had it pre-scripted, but you got me instead. And that gives you 0.1108 to 4 decimal places. Last one. This is definitely one that you'll get in the exam 1 kind of thing without your calculator, because it says find the probability of at least 1 from the 5 selections. Now the hard way is to do the 1 plus the 2 plus the 3 plus the 4 plus the 5. Let's not do the hard one. Let's instead think carefully and think, okay, well, bigger than or equal to 1 is everything except for 0. So let's do 1 minus the probability of x equaling 0. So 1 minus the probability of x equaling 0. We actually did this before. That's this one here, which came out being this. So we could have our 5c, whoops, excuse me, 5c is 0 times 4 over 7 to the power of 0 times 3 to the 5 over 7 to the 5. And that will give you 1 minus 3 to the 5 over 7 to the 5, which you could combine together with common denominators if you wanted to leave it with powers. But again, the numbers, again here, the size of the numbers will tell you it'll be exam 2 kind of thing. And that gives you 0.982. 5, 5. And that's a couple examples of how you work with the binomial distribution. Hope that helps.